So, are there any questions from what we discussed today? So again, it is a kind of an ambitious program in 2 hours to talk about so many different things, but I hope the ideas maybe stick with you, so the principles. So any questions about that? So we talked about diffraction, about how we break complicated problems in small ones, simple ones, how we add contributions from spherical waves and build a solution to an arbitrary source, and how that field propagates. That pretty much covers every diffraction problem you can think of. And then we found an approximation for the Fresnel regime, where we replace the spherical wave with the parabolic wave. Then we go even farther from the source, and then we got the Fraunhofer approximation, which gives us the field in far away from the source is the Fourier transform of the input field. That's very nice. And then, even better, we found that actually a lens does the same thing, and on a very short distance. So the z in the equation is replaced with the focal distance, so that means we can do this on a very compact physical space. So that allows us to do imaging and light scattering measurements, very, very practical on a benchtop. Then we move to scattering, which is kind of looking at three-dimensional objects and try to solve that problem. And in general, it's kind of complicated because now you have, under that convolution, you actually have the field that you're trying to kind of solve for. So the Born approximation takes care of that by assuming that if your object is very weakly scattering, like live cells or very, very dilute milk, the rule of thumb is if you can see through it, probably the Born approximation works. Okay, so it has to be very transparent. Then we can replace the field inside the medium with actually the initial plane wave that we put in. If we do that and then we look in far field, we obtain something very interesting, that the scattered field is the Fourier transform, the 3D Fourier transform of the object. Not only that, but I can take the Fourier transform inverse and actually get the formula for the object, provided that I measure the scattered field. So that's kind of the big deal with the Born approximation, that it gives you a way to solve inverse scattering problems when you know that the object is weakly scattered. Okay? Yes? Mean scattering, okay. What's the deal with mean scattering? So mean scattering...
Practically, when you reanalyze algorithm?
Mean scattering is useful in the sense that if you have a particle and you know it's a sphere and you know its size, the mean scattering gives you the full solution of the field scattered from that particle. No approximations. Okay? The particle can have absorption as well, a complex refractive index. What I was mentioning is that the mean scattering seems to be a little bit abused in our biophotonics field, in the sense that we tend to use it more than is legal. So sometimes we assume, oh, the cells are spheres or the nuclei are spheres, and then we apply the mean solution. So we have to be careful if that is okay or not. Okay? The solution to the mean scattering is actually a complicated combination of functions like this. It's not immediately transparent. It doesn't have that physical kind of intuition that comes with the Born approximation because it's a more complicated problem. The difference between, if you like, between the Born approximation and the mean scattering, the exact formula is that in the Born, we assume there is no ringing inside the sphere. So, you know, a sphere can act as a resonator. Actually, rooms can act as resonators, and probably you've heard of whispering gallery modes. Okay, so what happens is that you have waves that actually travel inside the spherical cavity. We have various wavelengths, and there are discrete modes that can exist. In the Born approximation, we say there are no modes. There is only the zero order mode. In other words, the phase shift through the particle is actually smaller than 2 pi. For an arbitrary sized particle, whenever you have a 2 pi phase shift, you actually get another mode and another mode and another mode. So that's why you get many of these resonances. Okay? Any other questions? Yep.
Why doesn't it bother us that the Born approximation violates the conservation of energy? So you can use it qualitatively?
It doesn't bother us in the sense that we don't measure, the total power is not of interest. What's of interest is the angular distribution of the scattered light. And that is pretty accurately described by the Born approximation. Okay, I mean we use triangles with two 90-degree angles all the time, right? It's kind of the same thing. So if you're trying to measure the total power, probably you have to be careful. But if you're trying to look how to see how the light is scattered at various angles, Born approximation is okay. The first order perturbation theory applies in many other branches of physics, so also in nonlinear optics. It's pretty useful, but we always have to be clear what goes into those approximations. Any other questions before we move on? So I'd like to tell you very briefly a few things about quantitative phase imaging, and I think I'm going to skip the holography part. Probably you can read it by yourselves, but this is kind of an introduction to what I'm going to present next week. But to me, it's also a way of combining imaging and scattering into one kind of the same common formalism. So I want you to think of the imaging versus scattering as kind of one and the same thing. It's just one is the representation in the spatial domain, the imaging. The other one is representation in the frequency domain, in the k-vector domain, right? So angular scattering. From the CD-ROM, I can image the tracks, or I can look at the diffraction orders. The information is kind of the same. Okay? So the reason light scattering people and light imaging people are usually different and tend to go to different conferences is that to go from imaging to scattering and vice versa, you need the phase of the field to do that connection, because this Fourier transfer relation is in terms of complex fields. So I'm trying to introduce this idea of doing quantitative phase imaging, so imaging something not only in terms of intensity but also phase of that imaging field. Then you can go back and forth as you like from imaging to scattering. So that's kind of my motivation for talking about this. And next week I'm going to show you actual results from our research. So probably I should skip the light microscopy or go very quickly, because you're going to have another lecture this afternoon by Professor Toussaint. But as you know, 1600 is about when the microscopy was first reported. The two main characteristics of a microscope are resolution and contrast. And one distinction I want to make up front is that resolution actually is, by itself, could be pretty useless unless you have contrast. So to understand that, think of a super high resolution microscope that is looking at something that's completely transparent, like particles that are index matched. Okay, so your microscope could give you 200 nanometer resolution, but you don't see anything. So resolution is kind of clear cut in the sense that we are going to write down a formula that gives you the far field kind of constraint. What's the final resolution you can get with far field microscopy? Due to Abbe's formula back in 1873. The contrast actually is a little bit more delicate. And in fact, people stopped worrying about resolution since 1873 until about 10 years ago. They thought the limit of lambda over 2, that's it. It's not worth spending time on it. While contrast methods actually kept developing. So if you look at the history of microscopy, you see dozens and dozens and dozens of methods kind of aiming at generating contrast, either by developing contrast agents, so visible structures or visible molecules of fluorophores that attach to structures in the object of interest, or try to enhance the intrinsic contrast of the object by understanding better how light interacts with the structure, using interferometry, using all optics tricks. So there are two kinds of contrast, endogenous and exogenous. And quantitative phase imaging is actually of the first kind. We don't want to add anything to the cells or tissues. We just want to understand better how light interacts with that structure and obtain information that way. There are some advantages to that you don't disturb the cells or the structures of interest. You can image them indefinitely for a week, up to you. You don't have the problems from fluorescence or photobleaching, phototoxicity, and so on. But you give away specificity, obviously. And in fact, it hurts me to say, but fluorescence microscopy is still the broadest technique today used in biology. And there are good reasons for that, is that fluorescence gives you access to specific information from the specimen, meaning I can tag a particular structure in the cell and only image that. I only make that fluoresce. So, in terms of endogenous contrast methods, dark field phase contrast, Schlerin, and later quantitative phase imaging, you can also do confocal microscopy without fluorescence, although that's less common. And also, you can have fluorescence that is actually occurring naturally from the cells. You're going to have I think later lectures on second harmonic generation microscopy from the tissue. That's also an endogenous contrast method. And of course, in terms of exogenous contrast, you have staining, fluorescence, but now more recently, there are these kind of new structures that you can use as contrast agents. And you're going to hear some talks about these throughout the week. So things like quantum dots, nanoparticles, strange structures. So here's the problem with seeing a transparent object. The problem is that the field passing through that object, so imagine this is your cell here and I send the light through it. The field that goes through, let's call it U, pretty much looks like an amplitude e to the I phi of x and y. Meaning there is no structure in the amplitude. The amplitude is constant. All the information about the structure of the object is in the phase. So if you just put your camera there and take the modulus square of this, you lose all the x and y information and you end up with a constant amplitude, constant intensity. In simple terms, this is the problem with imaging, for instance, most of light cells, that there is no amplitude information. They don't absorb light a lot or scatter a lot of light. All they do is they change the wavefront of the light coming in. Barely, but still. A lot more change in the phase than in the amplitude. So, so quantitative phase imaging is trying to quantify that phase. So the idea is to combine some important concepts from Abe, who, as I mentioned, wrote the first theory of microscopic imaging and published it in 1873. The idea was that actually an image is an interference, is the result of an interference process, as we just described earlier, right? So I take each point in my object, kind of scatters light or has its own spherical waves. An imaging system takes all that light and kind of brings it back together. So that's an interference process. So in writing the resolution theory, Abe kind of put out this concept that was new back then. A few decades later, Zernike actually used that idea to generate phase contrast microscopy, meaning try to get some information from here and couple it back into the amplitude, doing some kind of interference. And he managed to do that, and as you probably know, phase contrast microscopy is now common to all biology labs, for which Wernicke received a Nobel Prize in 1953, Nobel Prize for Physics. And finally, another idea is the idea of holography, developed by Denis Gabor, and he also received the Nobel Prize in Physics in 1971. So phase contrast developed in the 30s. This was first published in 1946, first holographic paper. So what we're trying to do is combine all these ideas. Imaging as an interference, phase contrast idea, but also holography, which means kind of quantifying the phase information of the field. So that's what what QPI is about. The end result is to get an image like this. This is, in particular, this is a neuron, where at each point in the image you get path length information. These are nanometers of optical path length at each point in the image. So this is the highest point. That's something that I didn't know about, that the nucleolus actually has a refractive index that's close to that of glass. And each cell seems to have that there. Of course, if you have this information, then you can process it in various ways. And for instance, you can take the gradient of this and you get something that's also very, very high contrast, but you give away the quantitative feature. The reason I like to show all this processing is that there are optical microscopes that give you optically this kind of image. This is called a Nanoscale microscope, where this this gradient image is provided optically. You take two replicas of the same image and you shift them barely and you interfere them and you get something like this. What I'm showing here is that once you measure the quantitative phase somehow, I'm going to tell you a few ways to do it, then you can numerically generate all these other methods. For instance, the first order derivative gives you this artifact, right? You see bright edges here, dark edges. The reason is that if you have, let's say, a tube like this or an edge, the first order derivative is highly positive, and then on the other side is highly negative, right? It goes up and then goes down. So that's why you have very bright and then very dark. The biology, and this is what the optical Nanoscale microscope that does this optically. This is what the biologists call, conveniently, the shadow artifact. It's a problem that you have to put up with. So we thought, hey, from here I can actually do a second order derivative and kind of make this not as bad. So look at the second order derivative. This is the Laplacian. In my opinion, it looks better than this. So now the artifact is gone. The artifact would be now when the edges change curvature, when you have something that goes from this to that. That's the second order derivative. So that's kind of, depending on what you're trying to do with the images, you can do various numerical processing. Probably the most, one of the most interesting things about quantitative phase imaging is that if you have the phase and amplitude image of a structure, like this, then you can use, under the Born approximation that we just talked earlier, the Fourier transform of that field gives you the scattering map of that structure. So now I want you to think about something. Usually, the scattering measurement is like this. You send the plane wave onto, let's say, this little particle, and then you're trying to measure in far field all this, let's say, the intensity at each angle. So think about this. If I give you a 1 micron particle, and I'm asking you to do an angular scattering measurement on that 1 micron particle, do you have any idea how hard that is? But think about it. So you take the cross-section of a 1 micron particle. The particle is weakly scattering to begin with. It's very, very difficult. You end up with a handful of photons along each direction. So when you go with your detector around the object, basically you are out of light when you go to very small particles. It's the same thing is true for if you try to measure scattering from a single cell. So So that's why you don't see a lot of measurements. People have tried, but it's not a good measurement to do. You require insane sensitivity. But it's very easy to see a 1 micron particle. So I want you to think about that a little bit. It's very hard to measure light scattered from one micron particle, because you take all that light that is scattered and you spread it in 4 pi, right, in all directions. But it's very easy to see the particle if you're looking in the image plane, meaning when you're detecting all that light in one place. So, the only condition is that when you measure in the image plane, you measure both amplitude and phase. For one thing, if your particle is of low refractive index, like 1 micron polystyrene bead in water, you can't even see it. If you measure the power of that image, the intensity image, you basically get almost nothing. So you do have to measure phase and amplitude. But if you do that, then the result is incredible. For instance, what I'm showing here, this is a piece of the dendrite of a neuron. This will be pretty impossible to measure going with a detector around the little dendrite, right? But if I measure this phase and amplitude, the Fourier transform of that, I should have made it in color. If you take a profile through here, I'm not sure if I have it. I don't. You have orders of magnitude of dynamic range, so you can measure very broad angular scattering from such a tiny transparent structure. So what I'm trying to tell you is that quantitative phase imaging gives you access to remarkable sensitivity in terms of scattering. So you can interpret your data as scattering, provided you are under the Born approximation and that you measure the complex field, not just the intensity. I want to point out 2 confusions about this field. Probably for those of you who read the optics journals, you may notice that there are many methods of quantitative phase imaging pretty much every week being developed, and so on and so on. And there are 2 big confusions that still persist in the literature. One is people talk about nanoscale, and one is about 3-dimensional. So we should not use nanoscale resolution in this case. We only should use as nanoscale sensitivity. Meaning, if I have this structure right here, or whatever right here, I am very sensitive to nanometer scale displacement. Meaning, if you measure the path length shift with an accuracy of lambda over 1,000 or something like that, that means you will be sensitive to 1 nanometer displacement. If something swelled up by 1 nanometer, you will be able to pick it up. So there is no question that quantitative phase imaging has nanoscale sensitivity. But we should not call it resolution. Because resolution means if you give me 2 objects separated by 1 nanometer, then I will be able to tell apart. And I would love to be able to say that we can, but we cannot. That's impossible. So nanoscale sensitivity, that's the easier one. I think the more confusing one is the 3-dimensional. And I think this idea goes back to holography, that somehow if you ask like a non-scientific person what they know about holography, is that it's 3D. In the same way, if you're talking about the 3D movies nowadays, they will tell you Avatar is 3D. But what we as optics people mean by 3D imaging is actually resolving an object in all 3 dimensions. So I have the refractive index as a function of x, y, z. Now in Avatar, you're using this parallax idea, the idea that you have 2 eyes and not only 1. But if you do this, then the 3D disappears. As far as we're concerned, we should not call that 3D. Same thing with holography. A hologram, probably you've looked at holograms, right, written in glass and whatever. So it looks, the field appears 3D is because of this illusion, because of your brain trying to piece things together. But if you do this, it disappears. So because of that, because we tend to plot our cells, for instance, this red blood cell, we can plot it as a surface plot like that. people call it 3D, but this is not 3D, you see? It's empty here, there is nothing here. 3D is tomography, it's something like this that you couldn't show in one image. It's like your MRI, right? So this is different Z sections. So there's a difference probably between the 3D field, so the fact that I have a 3D propagating field, X, Y, and Z, but that's not to say that I have the 3D object. So I think that's very important. So if you want to do a 3D reconstruction of an object, you need to do some other work. You need to get more data, more than one phase and amplitude image. Okay? Are we clear on this? Okay, so when you hear about 3D imaging, maybe make sure what's 3D. What kind of 3D are we talking about? 3D imaging means the 3D structure of the object, not the field. I'm going to let you read holography by yourselves. And I'm going to tell you a little bit how we measure this phase. Okay? So this is what I call the principles of Qpi. So, as I mentioned, if I take the modulus square of a complex field, the phase disappears. So right there, that's not a good way to do that, to get the phase information. So we need to mix at least two fields somehow, right? So we need to do interference. So I take the imaging field, UI, and I add to it a reference. And when I take the modulus square of that, I end up with the modulus square of one, modulus square of the other one. And then the interesting part, which is 2 times modulus of which, and cosine of something that has the phase difference between them under the cosine as argument. So I want you to kind of take a minute to think about the meaning of this phase, that actually we can never measure the phase of a field by itself. We can only measure phase differences between one field and some other field. Why? Because for one thing, the phase of this field coming out of this projector actually oscillates at the femtosecond level, right, at the scale. So we never measure that. What we measure, we take a piece of that and another piece of it, and then interfere them. We overlay them. So we measure phase differences. Okay, now I can have the reference field be shifted in time with respect to the imaging field. Okay, so I have two fields overlap, but now I can delay one with respect to the other one. So let's call that time modulation or phase shifting. But I can have another thing where the modulation is actually in space. So I can have this field coming like this and then one at an angle. So that's what gives you interference fringes. So the K of one and the K of the other one are not parallel. They are coming at an angle. So we call that off-axis interferometry. You call this an axis and this one is off-axis. So in the first case, so these are classes of methods, okay? You can do all kinds of variations around this, but I'm trying to give you kind of the bottom line. So I have an imaging system. This is my specimen. This is my image. By itself, if I take the image, intensity image of that, the phase is lost. But now I come with the reference field right here, plane wave. I overlay it on top of my image. And the trick is now to be able to have control on the phase shift of one with respect to this other one. So in other words, in the cosine right here, I am able to play with this. The final goal is to get this. But if you look at this equation, this is one unknown, this is another unknown, one unknown, two unknowns, three unknowns. So I have to do 3 or 4 measurements to get that. So how do I do more measurements? Well, I'm shifting the reference field in increments of quarter wavelengths, let's say, or pi over 2. And I'm doing a sequence of measurements, and then I'm combining them properly. So let me show you how that works. I'm measuring the intensity with zero phase shift between the two. So the reference field is not shifted. They're both in phase. I subtract the intensity obtained if I shift by pi. So the idea is I have one cosine, by shifted by pi, that gives you minus cosine. And then pi over 2, that gives me sine. 3 pi over 2 minus sine. So from 4 measurements, I take 2 pairs, subtract them, and then I take the ratio, and that gives me the argument. It's kind of incorrect, but you can think of this as an arctangent. I have sine over cosine, arctangent of that. The problem is that arctangent is only defined, is a bijective function only from, do you remember, from high school? Thank you, minus pi over 2 to pi over 2. So that means I can only recover phase on this half a circle, meaning that if the sine and cosine are both negative, it will be the same as if they're both positive. So that's why correctly you to put here argument. Or in MATLAB you put arctangent 2. So in that case it covers the whole circle. That's kind of a detail. So do you see the idea? We have this. This is the measurement. I measure this intensity. But because I have 1, 2, 3, the phase is the third variable, but as I just demonstrated, the phase kind of acts as 2 unknowns. 1 unknown for each half a circle. So basically, if I want to recover the phase of the entire circle, I need 4 measurements. How do I do that? Well, I shift this delay of the reference beam. So I make this 0, pi over 2, pi, and 3 pi over 2. I combine the 4, and I get the phase this way. You can think of it as me shifting along a sinusoid. 1, 2, 3, 4. That's wrong. It should be here. If you measure here and here, it's the same thing. Any questions about this? We call this phase shifting. This is a traditional method developed many decades ago. It works. But you notice you need to measure 4 times. So your measurement is in series. 1, 2, 3, 4, then get the phase. 1, 2, 3, 4, then get the phase. So another way of doing this, if you want to make faster measurements, is to do this off-axis idea. So now I have the image field right here, but now I come with the reference field at an angle. In that case, what you get actually is intensity of one, intensity of the other one, 2 times blah, blah, blah. Cosine of this delta k is actually the k vector difference. So it's as if I have these 2 k vectors. They give me an interferogram this way, right? Along x. And this is the phase of x and y that I'm after. And it turns out that we know how to do this, how to extract from one single shot measurement of this interferogram gives me the phase in one shot. We know how to do that. So the idea is to treat this as a signal in X. This is the real part of your signal. And basically do a Hilbert transform to get the imaginary part of that signal. You combine the two, you get the argument again. So the difference between phase shifting and off-axis is that the modulation is in time here. It's the same at all points. But now when you do off-axis, you add a modulation that is in space. So you're using the fact that you have a 2-dimensional detector, and that accounts for multiple measurements. So this is single shot. The other one is a series of 4 measurements. So you may say right away that this is better, right? Well, not so fast, because there are other characteristics that go into this. One question that comes up all the time is, what happens if your object has a phase shift, produces a phase shift that's bigger than 2 pi? And here's an example. This is an optical fiber immersed in, I forgot, glycerol or something. So as you can tell, it's very, very transparent. If you zoom into this little square here, you see the fringes. So this is the off-axis method. You see these little fringes here? They're bent. So the information about the phase is in that bending of the fringes, right? When you do the Hilbert transform, so you go from a cosine to a sine, and then you get the phase, what you notice is actually that the phase goes up to 2 pi and then drops to 0, and then up to 2 pi and then drops to 0. This is called phase wrapping. It simply means that we only have access to the phase through these trigonometric functions that are always wrapped around one circle, right? So luckily there are numerical ways to actually fix this up, do phase unwrapping. So whenever you see that it drops by 2 pi, you bring it up together. So instead of doing this, you now end up with a phase that goes like that. So we're able to measure many, many pi's. So very, very large phase shift in this particular case. So phase unwrapping is not a big issue when you image live cells. Most of the cells don't even wrap. They don't go beyond 2 pi. But if you get that situation, you can actually fix it numerically. Of course, provided your signal is not too noisy. If you have, imagine now you have random noise on top of this thing, you may get errors. But, so this is a problem that deserves kind of attention, but there are solutions for it. So finally, if you want to look at phase shifting and kind of phase shifting and make it faster, one way you can do is instead of going ABCD and then ABCD and ABCD, you can do ABCD and then BCDA and then CDAB and so on. So we call that interlacing. Of course, the information is still kind of smeared over the 4 frames, right? But it will give you 4 times faster information. Now, what are the figures of merit? One is how fast you can measure. I just mentioned that. How fast you can acquire in time. The other one is how fast you can acquire in space, meaning one temporal resolution, the other one spatial resolution. So if you give me an image, and let's say I measure the phase shift associated with that field, what's the smallest thing that I can distinguish in X and Y? Well, the best you can do is actually the diffraction limit. And here it turns out that actually phase shifting methods automatically preserve the diffraction limit of your microscope. Right? Because you simply shift them in time, kind of whatever transverse resolution microscope gives you, that kind of stays in place. When you do off-axis, you need to be careful. You can make sure you preserve the optical resolution, but you might as well mess it up if you're not careful. So that's why the two phase shifting and off-axis are kind of complementary in a way. This is a little discussion about resolution and how phase actually can... Okay, let me explain what this is. If you have 2 points shown by the red curve here, the profile, that are barely resolved with the regular microscope, if you manage to control the phase on one with respect to the other one, you can actually make them look completely separated, like the blue line. If you make a shift of pi. With a shift of pi over 2, you get the red curve. With a shift of 0, you get nothing. They are not resolved at all. This is a little discussion that actually I would suggest you stop and think about it a little bit, that the resolution and intensity actually is defined by the Rayleigh criterion, so in a regular way. But when you introduce phase, then you probably need to think a little more about it. Yeah.
This is the third point.
Third point. Oh, yes. Then, off-axis method. Methods to preserve the diffraction limit. This discussion is somewhat different from preserving the resolution. This is saying that actually phase can affect how well 2 points are resolved. Phase difference between 2 points. So this is taken from Goodman's book on Fourier optics, for those who know the book. I would move forward and go ahead with the figures of merit. So spatial sampling, that means transverse resolution. Temporal sampling, how fast you can measure in time. But the important things about when you do quantitative phase imaging is how sensitive you are in that phase measurement. We mentioned nanoscale sensitivity, whatever. What does that mean? Well, again, you have a time sensitivity. So if I measure a movie, right? I take a movie of my cells. If I take a time profile, what's the smallest bump, phase shift that I can measure in time, measuring repeatedly, right? That would be temporal phase sensitivity. If I'm looking in one image like this, and you give me, let's say, a step in topography, what's the smallest step that I can resolve? I call that spatial phase sensitivity. And again, you'll see how various methods are actually complementary. These couple of slides here are about doing averaging and kind of, you can do band passing both in time and space. Those of you who are using mod-lock lock-in amplifiers are familiar with this. You can do the same kind of lock-in detection spatially to reduce noise by orders of magnitude. So if you're interested, you know something is going to happen in your cell at the 1 micron scale, then you can filter all the information around that spatial frequency. And from a noisy measurement, you can actually get very high sensitivity. So let me show you a table in the end. This is what I want to show you, and I'm going to finish here. So when you see new methods for doing QPI, maybe try to think of this table. So these are the features: acquisition rate, transverse resolution, temporal sensitivity, spatial sensitivity. And the fact that actually there are classes of methods that fulfill one of these directly without any other precautions. So off-axis is fast, therefore it gives you acquisition rate. Phase shifting, as I mentioned, preserves the diffraction limit, so that's transverse resolution. Common path method, the idea that the two interfering beams are actually physically overlapped as much as possible. This basically makes the noise in the two beams to cancel out. When you're doing an interference, you do U1 times U2 conjugate, that noise goes away. So that gives you high temporal sensitivity. Finally, lasers are not the greatest imaging tools because they give you speckles, meaning spatial sensitivity is low. It is noisy spatially. So in our lab, we now actually developed some white light methods that kind of diminish the speckles a lot. So now white light can give you spatial sensitivity like no other methods. So the funny thing is, when you see various methods published in optical letters every week and so on, is that how is it that with these 4 features we get so many methods? Well, you can combine 2 by 2. So you get combinations of the 4 taken by 2, you get 6 possible combinations. So you can do off-axis and phase shifting and white light, blah, 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 blah. You can combine 3 of them, then you get 4 possible combinations. I'm not aware that anybody combined all 4 of them. White light, phase shifting, off-axis, and common path is doable, but it would be an overkill. So they accomplish different tasks. So in our lab, we do this also, depending on what we want to do with the instrument. But the net result is something like this. So again, this is the neuron I showed you earlier. You want this background to be flat, right? So you can, these are nanometers of optical pathing, so you can become very sensitive to these path length changes. So this is a white light method, that's why the background is so low. If it's common path, then it's very sensitive in time. So if I sit in one point here, I'm going to be able to monitor when a little vesicle is passing by or something like that. And this happens to be diffraction limited preserved from the microscope. So this is the best you can do with that objective. So in this particular case, I'm going to talk more about this Monday. We give up acquisition speed. So this is a phase shifting method that actually only can acquire 2 of these a second, which for most applications is okay, but if you want to look at, I don't know, how this neuron is firing an action potential, this wouldn't work. Okay, so what I'm trying to tell you is that there is no perfect method, but I think we have that table is kind of the structure where all the methods are trying to fit in. So those are the figures of merit and the various approaches to fix it. So I'm going to stop here and ask you for questions. You are going to see actual results next week, but I thought just an introduction to the kind of the field.
I know that you skipped it, but I have to ask you, how is that different from holography? I mean, the interference term that you've written is effectively the term that you also.
Yeah, so the off-axis method is what is called digital holography, right? The difference with the traditional holography was basically developed to not to measure in the image plane, because for macroscopic objects like something in this room, the image plane is not defined, right? The objects are big. So for microscopy, the good thing is that now the objects are thin. You can define a plane of focus and actually image it. So measure the interferogram in the image plane as opposed to somewhere in the Fresnel plane and then do numerical propagation to get the image out. But the idea is like it's the same. Holography means measuring the phase information.
So I heard people talking about image hologram. So that's probably then.
Okay, image hologram is of fact, yeah.
And how does the four shifts with what you said about sinus cosine being projected?
Yeah.
How does it work with three-phase shifts? I mean, you have methods that use only three-phase shifts and that need a separate exposure.
So I have many discussions with people with the three-phase shifts all the time. Why is it that we're using 4 and not 3? And my answer is, if you know your phase is below 1 pi, then you are okay with 3 phase shifts. If you want to recover the whole circle all the time without any constraints, you need 4. That's my answer to that. So it's kind of funny. Holography should include, in general, holos means everything about the field, whole information about the field. But phase shifting, for instance, doesn't fall under holography, right? Usually, when you do phase shifting, people don't call that holography. I even heard the interferometric holography more recently. So, to me, digital holography is one way to get quantitative phase images, but there are others. So, other questions? Yeah.
Is it because
Spatial sensitivity.
Not resolution?
Not resolution. So we're talking about the noise, phase noise, spatially. So if I measure, imagine an empty field of view, the speckles will give you a very noisy background. So the standard deviation of the phase measurement will be high. If you use white light, it's getting lower.
Is it because lasers are very coherent?
Right.
Okay.
Yep.
During this kind of high quality phase images, is
Yep.
there any minimal scenario to maintain, or is there anything that has to be made sure to get good phase images?
So again, what I mean by good, what I try to narrow it down by good is these 4 kinds of good. Okay, so which good are we talking about? It depends on what you want to do. For instance, we used lasers for many years just fine to measure fluctuations in red blood cells. No problems there. They were common path, the methods. They were very sensitive temporally, and that's all you need for red blood cells. You don't need super high details in the cell because they don't have much structure. So we could do that here. But now I wanted to look at transport inside other cells, and then we couldn't do it with a laser, so we had to do it with white light. So this was missing. So it depends on your application. Other questions? If not, thank you very much. We'll take a few minutes break, and then we'll come back to Professor Toussaint's talks. Thank you.